Look up at the night sky. What do you see? A scattering of stars, perhaps a planet or two, the faint glow of distant galaxies. But what if I told you that beyond those pinpricks of light lies a universe filled with mysteries so profound they defy even the brightest minds on Earth? We've sent probes to the edge of our solar system, built telescopes that peer billions of years into the past, and yet the cosmos still holds secrets that leave scientists utterly baffled. From galaxies that shouldn't exist to signals that echo from the void with no explanation, space is a puzzle box with pieces we're only beginning to touch. Think about this for a moment. We live in an era where technology lets us map the human genome, create artificial intelligence, and even manipulate particles at the quantum level. But when it comes to the universe, we're still staring into the dark, wondering. Take dark matter, for example, an invisible force that makes up nearly 27% of the cosmos, yet we've never directly observed it. Or massive cosmic structures so large they challenge our very understanding of physics. These aren't just scientific curiosities, they're gaping holes in our knowledge, reminders that for all our progress, the universe humbles us at every turn. And that's exactly what makes this journey so thrilling. Today, we're diving into 25 of the most mind-bending unsolved mysteries in the cosmos, phenomena that defy logic, tease our imagination, and might just rewrite the laws of reality as we know them. Some of these enigmas could hide clues about the origins of life itself, while others might force us to rethink everything we thought was true about space and time. So whether you're a seasoned stargazer or someone who simply loves a good mystery, buckle up, because the universe is about to take you on a ride stranger than fiction, where every answer leads to a deeper, more tantalizing question. Ready to explore the unknown? Let's begin. What if we have been contacted by aliens and we missed it? That's the spine-tingling question behind the wow. Signal, one of the most tantalizing cosmic mysteries ever recorded. Back in 1977, a radio telescope in Ohio picked up a blisteringly strong burst of radiation, a signal so precise it seemed engineered. It lasted 72 seconds, just long enough to freeze the astronomer who discovered it in stunned silence. He scribbled, "Wow," in the margins of the data printout, giving the signal its name. But here's the kicker. It was broadcasting at exactly 1,420 megahertz, the natural frequency of hydrogen, the most common element in the universe. A cosmic calling card, maybe the real head-scratcher. We've never heard it again. Not once in nearly 50 years of searching. Scientists have torn apart every possible explanation: comets, satellite reflections, even secret military tests, but none fit the data. The signal came from the direction of the constellation Sagittarius, where there's no known star or planet that could have produced it naturally. Some theorists argue it was a one-time interstellar flare, like a cosmic burp. Others whisper about alien beacons, a deliberate transmission meant to say, "We're here, and the hunt isn't over." Projects like Breakthrough Listen now scan the skies with AI, sifting through static for another whisper from the void. But until then, the wow signal remains a ghost in the machine, a fleeting, electrifying hint that we might not be alone. The universe sent us a message. We just don't know how to answer. Now picture this, an entire cosmic scaffolding, invisible yet holding galaxies together like ghostly glue. That's dark matter, the universe's most frustratingly elusive ingredient. We know it's there because without it, galaxies would spin themselves apart. Stars on the outer edges of spiral galaxies move way too fast for the visible matter alone to keep them anchored. Something unseen, something massive, must be weighing things down, and not just a little. Dark matter outweighs ordinary matter 5 to 1, making up roughly 27% of the cosmos. Yet here's the cosmic irony. Despite its overwhelming presence, we've never seen it. No light, no radiation, no interaction with electromagnetic forces. It's like trying to catch smoke with your bare hands, but scientists aren't giving up. Deep underground in abandoned gold mines and beneath mountain ranges, detectors like the LUXZEPLIN experiment hunt for faint whispers of dark matter particles. These ultra-sensitive devices wait in perfect darkness, shielded from cosmic rays, hoping to catch the rare moment a dark matter particle bumps into an atom of liquid xenon. Leading theories suggest dark matter could be made of WIMPs, weakly interacting massive particles entities that barely acknowledge ordinary matter except through gravity. But there are other suspects too: actions, sterile neutrinos, even primordial black holes from the universe's first second. The stakes couldn't be higher. Crack this mystery and we might finally understand why galaxies form the way they do, or uncover entirely new physics that rewrites the rulebook. Until then, dark matter remains the universe's ultimate hide-and-seek champion. We feel its pull in the dance of galaxies, measure its shadow in the bending of light around cosmic voids, yet it slips through every net we cast. One thing's certain: the day we detect it won't just solve a puzzle, it'll open a door to the hidden 95% of reality we're still blind to. If dark matter is the universe's invisible scaffolding, dark energy is the enigmatic force ripping it apart. Picture this: not only is the cosmos expanding, but that expansion is accelerating like a runaway train punching through the fabric of space itself. And here's the kicker: this mysterious energy makes up a staggering 68% of the universe, dwarfing even dark matter. Yet we have no idea what it actually is. The story begins in 1998, when two teams of astronomers studying distant supernova made a jaw-dropping discovery. These exploding stars, billions of light-years away, were fainter than they should have been, meaning space wasn't just stretching, it was stretching faster over time. The implications were earth-shattering. Gravity should have been slowing the expansion, pulling galaxies back like a cosmic rubber band. Instead, something was overpowering it, pushing the universe apart with unbeatable force. That something, dark energy. Now the plot thickens. Einstein actually predicted this sort of. His equations included a cosmological constant, a fudge factor he later called his greatest blunder when Edwin Hubble proved the universe was expanding. But today, that same constant might be the key to dark energy, a property of empty space itself, where even a vacuum hums with repulsive energy. There's just one problem. When physicists calculate how strong this energy should be, their numbers are off by a factor of 10 to the power of 120. That's a 1 followed by 120 zeros, the worst mismatch in science. So what else could it be? Enter quintessence, a dynamic, evolving field of energy that changes over time, unlike Einstein's static constant. Think of it as cosmic weather, with regions of high and low pressure subtly tugging at spacetime. Some theories even suggest dark energy might interact with dark matter, or that our understanding of gravity itself is flawed. The stakes astronomical. If dark energy grows stronger, it could tear apart galaxies, then atoms, in a big rip. If it fades, gravity might crush the universe back into a singularity. Or maybe it's just the first hint of a deeper layer of physics waiting to rewrite our cosmic story. One thing's certain: dark energy isn't just a mystery, it's the ultimate wildcard in the fate of everything. The universe is unimaginably vast, trillions of stars, countless planets, billions of years for life to arise. Statistically, we shouldn't be alone, so where is everybody? That's the Fermi Paradox, a question so unsettling it keeps astronomers awake at night. Named after physicist Enrico Fermi, who famously blurted out, "But where are they?" During a lunchtime chat about aliens, this paradox pits probability against silence. The math says civilization should be common, yet the skies are eerily quiet. Consider the numbers. Our Milky Way alone houses around 100 billion stars, many with planets in the so-called Goldilocks zone, not too hot, not too cold, just right for liquid water. Even if only 1 in a million planets developed intelligent life, we'd still have thousands of civilizations out there. Some could be millions of years older than us, with technology beyond our wildest sci-fi. So why no alien radio signals, no megastructures, no interstellar postcards? Enter the Great Filter, one of the most chilling theories in science. It suggests there's some catastrophic hurdle that prevents life from reaching the stars, and we might not have passed it yet. Maybe complex life is vanishingly rare, or perhaps intelligent species always self-destruct through nuclear war, climate collapse, or rogue AI. The terrifying possibility. We're not special, just next in line for extinction, but not all explanations are doom-laden. The zoo hypothesis proposes advanced civilizations are out there, quietly observing us like animals in a cosmic nature preserve. Others think interstellar travel is simply too slow or too costly. Even with warp drives, crossing galaxies could take millennia. Or maybe we're like ants trying to spot airplanes. Alien tech could be so advanced we wouldn't recognize it. Then there's the dark forest theory, inspired by the silence itself. Imagine the universe as a forest where every civilization hides, fearing that any signal, any flicker of existence might attract predators. If that's true, our own radio broadcasts could be a deadly mistake. So is the paradox a warning or a puzzle, a test of our survival or proof of our solitude? Until we find even a single microbe beyond Earth, the question hangs over us, a humbling reminder of how much we don't know. The stars may be teeming with life, or we might truly be the universe's first, lonely attempt to understand itself. Either way, the silence speaks volumes. Imagine a flash of radio waves so intense it outshines entire galaxies for just 1,000th of a second. That's a fast radio burst, one of the cosmos' most electrifying puzzles. These bizarre blips of energy were first spotted in 2007, buried in old telescope data like cosmic Morse code nobody noticed. Now we know they're happening all across the universe, some unleashing as much power as 500 million suns in less time than it takes to blink. And the mystery runs even deeper. Most vanish instantly, never to repeat, but a handful like the infamous FRB 121102 keep crackling from the same patch of sky, like a celestial alarm clock we can't snooze. So what's firing these intergalactic bullets? The suspects range from apocalyptic to downright eerie. Leading the pack are magnetars, super dense, spinning corpses of dead stars with magnetic fields so strong they'd rip the electrons off your atoms from 1,000 miles away. Picture one of these neutron stars having a starquake, its crust snapping under magnetic pressure like a cosmic twig, sending shockwaves through space-time. That could explain some bursts, but what about the repeaters? One theory suggests they might be powered by highly magnetized planets orbiting these zombie stars, their orbits occasionally triggering explosions like cosmic dynamite. Then there's the wild card, FRB 202206110A. Detected in 2022, this monster came from 8 billion light-years away, so far back in time, Earth hadn't even formed yet. Its sheer distance means whatever created it must be unimaginably powerful, possibly involving mergers of black holes or neutron stars. But here's the twist, it hasn't repeated. That puts it in the same enigmatic category as one-off bursts, which might have entirely different origins, perhaps even cataclysmic events where the source destroys itself in the process. And yes, some still whisper about aliens. A civilization advanced enough could theoretically beam focused energy across galaxies, using pulsars as lighthouses or even propelling light sails with these radio wave bullets. But here's the catch, the bursts are spread across the universe, coming from all directions. For aliens to explain this, virtually every galaxy would need extraterrestrial engineers blasting signals, an idea most scientists call a last resort hypothesis. The real breakthrough, we're finally starting to trace these bursts home. In 2020, astronomers linked an FRB to a magnetar in our own galaxy, confirming at least one source. Yet the repeating bursts still defy easy answers, flickering in patterns that look almost intentional. Whatever they are, fast radio bursts remind us the universe is far stranger than we dreamed, and every time we catch one, it's like intercepting a fragment of a cosmic conversation we're only beginning to decode. Some stars flicker like candles in the wind, but none dance as erratically as Tabby's star, a cosmic oddity that's defied explanation for nearly a decade. Officially catalogued as KIC 8462852, this unassuming star in the constellation Cygnus first made headlines in 2015 when citizen scientists flagged its bizarre behavior. Unlike typical stars which dim in predictable, rhythmic patterns when planets pass by, Tabby's star plunges in brightness by up to 22%, in jagged, irregular dips that look less like planetary transits and more like someone's flipping a cosmic light switch. The initial theories ranged from mundane to mind-blowing. Could it be a swarm of comets, a colossal dust cloud, or, as some dared to suggest, an alien megastructure, a Dyson sphere built by an advanced civilization to harness the star's energy? That last idea sent shockwaves through the scientific community, not because it was likely, but because we couldn't immediately rule it out. The star's light patterns didn't match anything seen in nature, and the dips seemed too extreme for ordinary astrophysics. Follow-up observations only deepened the mystery. In 2017, the star dimmed again, this time in slow, dramatic waves that ruled out solid objects like planet fragments or asteroid belts. Spectroscopic studies revealed the dimming was wavelength-dependent, meaning shorter wavelengths of light were blocked more than longer ones that pointed squarely to dust, fine, diffuse particles smaller than a grain of sand, likely from cometary debris or interstellar material passing between us and the star. Yet the plot thickens. Tabby's star has also been gradually darkening over the past century, a fact uncovered by examining century-old photographic plates. No known natural process explains both the long-term dimming and the sudden, erratic dips. Some researchers propose a massive collision in the star's asteroid belt, unleashing clouds of debris that still haunt its orbit. Others speculate about a rogue planet being torn apart by gravitational forces, its remains casting fleeting shadows, and then there's the wild card, magnetic activity. Some stars with hyperactive magnetic fields produce starspots so vast they blot out huge swaths of light. But Tabby's star isn't behaving like those known variables. It's cooler than the Sun, yet its fluctuations are far more violent than any magnetically active star we've seen. So where does that leave us? The alien megastructure theory, while tantalizing, remains a last resort. Occam's razor suggests dust is the culprit, but dust with a twist. Recent studies hint at an uneven, clumpy distribution, possibly stirred by an unseen planet or binary companion. Others suggest the star itself might be consuming a planet, belching sporadic dust clouds as it digests its meal. One thing's certain, Tabby's star isn't done surprising us. Every time we think we've pinned it down, it throws another curveball, reminding us that the universe loves a good mystery. Whether it's cosmic dust, magnetic monsters, or just maybe something even stranger, this star challenges us to think bigger, dig deeper, and stay humble in the face of the unknown. Imagine this: two robotic pioneers hurtling into the void with messages for any aliens who might find them, gold plaques bolted to their sides, etched with symbols of humanity. Pioneer 10 and 11, launched in the early 1970s, were humanity's first spacecraft destined to leave the solar system. But as they drifted farther from Earth, something bizarre happened. They began slowing down, just a tiny bit, but enough to make physicists rip up their equations. This was the Pioneer anomaly, a cosmic detective story that took decades to solve and still leaves unsettling gaps in our understanding of deep space. At first glance, the numbers seemed trivial. Each probe was decelerating by about 9,000ths of a centimeter per second, squared less than a billionth of the gravity you feel right now. But over years, those fractions added up. By the time Pioneer 10 reached the edge of the asteroid belt, it was hundreds of kilometers off its predicted course. The kicker: this wasn't supposed to happen. Newton's laws and Einstein's relativity had governed spacecraft navigation flawlessly for decades. Either something was pushing the probes backward, or our grasp of physics had a blind spot. Cue the theories, each wilder than the last. Could it be dark matter's gravitational tug, a glitch in our understanding of inertia at cosmic distances, or the most tantalizing evidence of a fifth fundamental force, an unknown interaction undetectable here on Earth? For years, the anomaly became a playground for radical ideas, a crack in the foundation of classical physics where new theories could squeeze in. Then came the breakthrough: heat. Not from some exotic source, but from the probes themselves. Pioneer's nuclear power generators warmed its body, and that heat radiated unevenly off its dish-shaped antenna. Like a car's exhaust pushing backward, those infrared photons carried momentum just enough to account for the mysterious deceleration. Case closed, not quite. While thermal radiation explained most of the anomaly, later studies revealed discrepancies. The probes slowed slightly more than the heat calculations predicted, leaving a whisper of uncertainty. And here's the haunting part: we may never know why. Pioneer 10's signal faded in 2003, and 11 went silent in 1995. Their data is all we have, frozen in time like cosmic fossils. Today, the anomaly serves as a humbling lesson. Even in the era of precision spaceflight, the universe reminds us how much we don't know. Future missions like those to Pluto or the Kuiper Belt now account for this thermal recoil effect, yet no one can say for sure if we've caught every variable. Deep space might still hide forces we've yet to name, nudging our probes in ways we can't yet measure. The pioneers were meant to be messengers to the stars. Instead, they became messengers from the void, carrying back a puzzle we're still piecing together. In October 2017, astronomers spotted something that shouldn't exist: a fast-moving, cigar-shaped object tumbling through our solar system. Named Oumuamua, Hawaiian for scout, it was the first confirmed visitor from interstellar space. But this wasn't just any space rock. Its bizarre properties ignited a firestorm of debate, pitting mainstream science against one bold Harvard professor who dared to ask, could this be alien technology? Let's start with the facts. Oumuamua was unlike any asteroid or comet we'd seen. Its shape alone defied logic: a needle-like structure roughly 10 times longer than it was wide, spinning like a cosmic drill bit. Natural objects simply don't form that way. Most space debris is lumpy or spherical. Then came the real shocker: it accelerated. As it hurtled past the sun, something gave it an extra push, like an invisible engine firing. Comets do this when their ices vaporize, creating a visible tail. But Oumuamua had no tail, no detectable gases, no dusty halo, just pure, unexplained motion. Enter Avi Loeb, Harvard's controversial astrophysicist. While most researchers scrambled for natural explanations, Loeb proposed a radical idea. Oumuamua might be a light sail, a piece of alien tech designed to catch stellar winds, just like humanity's experimental light sail too. His arguments were met with eye rolls from peers, but the data was undeniably strange. The object's brightness fluctuated wildly, suggesting a flat, reflective surface. Its trajectory didn't match typical cometary orbits, and that acceleration, light pushing against a thin, artificial structure, could explain it perfectly. Not so fast, said skeptics. A team from the University of California later suggested Oumuamua could be a hydrogen iceberg, a chunk of frozen hydrogen gas sublimating invisibly in sunlight, providing thrust without leaving traces. Others proposed it was a shard from a Pluto-like planet, sheared off in some ancient collision. The problem: we've never observed hydrogen icebergs, and planetary fragments don't usually look like interstellar pencils. The debate boils down to Occam's razor versus imagination. Is Oumuamua a freak natural object, the first of its kind we've stumbled upon, or is it evidence that we're not alone, a discarded probe or derelict ship drifting between the stars? Either way, its brief flyby left us with more questions than answers. By the time we trained our best telescopes on it, Oumuamua was already too far away, vanishing into the void as mysteriously as it arrived. One thing's certain: the next interstellar visitor won't catch us off guard. Projects like the Vera Rubin Observatory now scan the skies nightly, ready to chase down the next cosmic oddity. Whether it's aliens or just another space weirdo, the universe has made one thing clear: it's full of surprises, and we've only just begun to take notes. Hidden behind the thickest part of our Milky Way, where starlight drowns in cosmic dust, something colossal is pulling thousands of galaxies, including our own, toward it at over 600 kilometers per second. Astronomers call it the Great Attractor, a gravitational monstrosity with the mass of tens of thousands of Milky Ways, bending the fabric of spacetime itself. But here's the catch: we can't see it. Our own galaxy's bulge blocks the view, creating a blind spot known as the zone of avoidance. It's like trying to study a hurricane while standing inside a thunderstorm. The discovery dates back to the 1970s, when scientists noticed galaxies in our cosmic neighborhood weren't just drifting apart from the Big Bang, they were all sliding sideways like leaves caught in a river's current. The epicenter of this mysterious flow, a patch of sky near the constellations Centaurus and Norma, but mapping it was like navigating a maze blindfolded. Dust and stars in the Milky Way's plane scatter visible light, leaving radio waves and infrared as our only eyes. Enter the Laniakea supercluster, a staggering cosmic filament that rewrote our place in the universe. In 2014, astronomers using advanced velocity mappings revealed that the Great Attractor isn't the final boss. It's just a hub within Laniakea, a sprawling web of 100,000 galaxies stretching 500 million light-years. Picture it as a colossal spider's web, with the attractor sitting near the center, gently tugging everything toward it, but the mystery only deepens. Recent X-ray observations peeled back some of the zone of avoidance's curtain, revealing galaxy clusters like Norma Cluster, massive enough to contribute to the pull, but not nearly enough to explain it entirely. Somewhere behind that cosmic veil, something even bigger might lurk, perhaps an unfathomable concentration of dark matter or a supercluster we've yet to map. The race to solve this puzzle is heating up. Projects like the Square Kilometer Array radio telescope aim to pierce through the zone of avoidance with unprecedented clarity, while space-based infrared observatories like the James Webb Telescope analyze hidden galaxies. Every new dataset chips away at the mystery, but the Great Attractor holds its secrets close. One thing's certain: this invisible titan isn't just pulling galaxies, it's pulling our curiosity into uncharted realms of the cosmos. Black holes aren't just cosmic vacuum cleaners, they're the universe's ultimate shredders, tearing apart stars and swallowing light itself. But here's where things get weird. According to Stephen Hawking's groundbreaking work, even these monstrous gravity wells aren't eternal. They evaporate, slowly leaking energy in the form of Hawking radiation, a ghostly glow of particles that escapes their grip over eons. Sounds poetic, right? There's just one catastrophic problem. If a black hole vanishes, what happens to all the information it swallowed? Atoms, planets, even the DNA of unlucky astronauts, everything that fell in would leave no trace, erased from reality like a chalkboard wiped clean. That's the black hole information paradox, a clash between relativity and quantum mechanics so profound it threatens the very foundations of physics. Let's unpack the nightmare. Quantum mechanics insists that information can never truly be destroyed. Even if you burn a book, the ashes and smoke preserve its information in scrambled form, theoretically reversible with godlike precision. But black holes defy this. Hawking radiation isn't a neat receipt of what fell in. It's pure thermal noise, random as static on a TV screen. No hidden patterns, no cosmic barcodes. If the black hole evaporates, the information is gone, violating quantum theory's sacred rule. For decades, this paradox split physicists into warring camps. Some, like Hawking himself, initially bet information was truly lost, a stance that would have rewritten physics. Others refused to believe the universe had such a glaring bug. Enter the holographic principle, a radical idea that might just solve the riddle. Imagine everything inside a black hole. Every atom, every photon isn't actually inside at all. Instead, it's encoded on the event horizon surface, like a cosmic DVD where 3D reality is projected from 2D data. This isn't sci-fi, it's math. In 2016, Hawking and colleagues proposed that Hawking radiation might carry subtle imprints of what fell in, etched into the radiation's quantum entanglement patterns. Picture it like a smoke signal, chaotic at a glance but with the right cipher revealing a message. Recent breakthroughs are turning theory into testable science. Experiments with quantum computers simulate black hole dynamics, while lab-grown, analog black holes in superfluid helium hint at how information might escape. Even gravitational wave detectors could someday spot faint echoes in merger events, ripples encoding lost data. The stakes, unifying relativity and quantum mechanics, or exposing a flaw in our understanding of spacetime itself. Here's the kicker: if information does survive, black holes aren't tombs, they're transformers, mangling reality into forms we're just learning to read. Every evaporated black hole might be broadcasting a faint cosmic tweet. Everything you thought was lost, it's still here, you just weren't listening. Imagine holding a moon rock in your hand, gray, dusty, seemingly ordinary. But hidden within its ancient crystals lies a secret that rewrites lunar history, traces of a magnetic field once as strong as Earth. Here's the puzzle. Today, the moon's magnetism is barely a whisper, a faint imprint in scattered rocks. Yet 4 billion years ago, this small world, just 1/80th Earth's mass, somehow generated a magnetic powerhouse. How and why did it vanish? The answers aren't just about the moon, they're a masterclass in how planetary dynamos live and die. First, the smoking gun, Apollo-era rocks. When astronauts brought back lunar samples, scientists found something astonishing. Certain rocks, like the famous Troctolite 76535, were magnetized, their iron atoms frozen in alignment like microscopic compass needles pointing to an ancient North Pole. This wasn't just residual magnetism from Earth's field, the intensity matched fields 10 times stronger than Mercury's current one. The conclusion: the moon once had a molten, churning core, spinning like a cosmic generator to produce its own magnetic shield. But how? Enter dynamo theory, the same process that powers Earth's magnetic field today. Picture a swirling cauldron of liquid iron in the moon's core, conducting electricity as it rotates. Movements driven by heat and rotation create electric currents, which in turn generate a magnetic field. On Earth, this dance is fueled by 2 engines, heat left over from planetary formation and radioactive decay. But the moon's small size meant its core should have cooled rapidly, shutting off the dynamo within a few 100 million years. Yet the rocks tell a different story. The magnetic field persisted for over 1 billion years. The solution might lie in a cosmic battering ram. One leading theory suggests the moon's orbit wasn't always so serene. Early in its history, gravitational tugs from Earth could have kept its core stirred, like swirling coffee in a cup, extending the dynamo's life. Computer simulations show this gravitational kneading might have generated enough heat to keep the core molten far longer than passive cooling would allow. Then, around 1 billion years ago, the music stopped. As the moon drifted farther from Earth, tidal forces weakened. The core began to solidify layer by layer until the dynamo sputtered out. The magnetic field faded, leaving the moon exposed to solar winds and cosmic rays, a key reason its surface is so barren compared to Earth's protected biosphere. But here's the twist. Some newer studies propose an even wilder idea. Colossal impacts might have given the moon's magnetism a second wind. When asteroid strikes like the one that formed the South Pole Aitken Basin rocked the moon, they could have unleashed tsunamis of molten rock, reigniting convection in the core for brief periods. Think of it as jump-starting a dead car battery with a cosmic collision. The implications stretch far beyond our moon. If small bodies can sustain magnetic fields through sheer orbital chaos or violent impacts, exomoons around distant gas giants might harbor hidden dynamos too, and with them, potential shields for alien life. Every magnetized moon rock is a time capsule holding clues not just to our past, but to the magnetic mysteries waiting on worlds we've yet to discover. At Saturn's North Pole, a shape defies nature's usual chaos, a perfect hexagon wider than two Earths with razor-sharp edges that have endured for decades. This isn't computer-generated or an optical illusion. It's a six-sided jet stream whipping around at 320 kilometers per hour, a geometric hurricane so precise it looks engineered. Discovered by Voyager in the 1980s and later confirmed by Cassini, the hexagon remains one of the solar system's most hypnotic puzzles. Theories about its origins read like a physicist's brainstorming session. On Earth, atmospheric patterns are messy cyclones spiral, jet streams meander. But Saturn's hexagon is a rigid, rotating polygon, its corners locked in place like a cosmic bolt. One leading explanation points to standing wave dynamics. Imagine wind shear different layers of atmosphere moving at varying speeds, creating instability. Under the right conditions, these instabilities can snap into geometric shapes, much like how vibrating water forms hexagonal patterns in a lab. Saturn's rapid rotation, a day that lasts just 10.5 hours, might act as a cosmic tuning fork, stabilizing the hexagon against the planet's turbulent weather. Yet the devil's in the details. Why 6 sides? Why not 5 or 8? Experiments with spinning fluids show hexagons can emerge naturally under specific conditions, but replicating Saturn's precise scale and longevity in simulations remains elusive. Some models suggest deeper forces at work, perhaps interactions between Saturn's outer atmosphere and hidden layers of conductive fluids beneath, amplifying and shaping the jet stream like an invisible hand. Earth's atmosphere offers no equivalent phenomenon, and for good reason. Our planet lacks Saturn's sheer speed and uniformity. Earth's surface, with its mountains, oceans, and uneven heating, disrupts large-scale geometric patterns before they can form. Saturn, by contrast, is a gas giant with no solid surface to break up atmospheric flows, allowing anomalies like the hexagon to persist. Even Jupiter's polar storms, while mesmerizing, appear as chaotic swirls, nothing as orderly as Saturn's masterpiece. The hexagon's endurance adds another layer of intrigue. Unlike earthly hurricanes that dissipate in days, this structure has outlasted every telescope pointed at it. Cassini watched it through seasonal changes, noting how its color shifted from blue to gold as Saturn's northern hemisphere entered summer. Proof that the hexagon isn't just a surface feature but a deep-rooted atmospheric engine. Could similar shapes lurk on other worlds? Exoplanets with rapid rotations and thick atmospheres might host their own geometric storms, invisible to us for now. Saturn's hexagon is more than a curiosity. It's a lesson in how fluid dynamics can sculpt the universe in ways we're only beginning to grasp. Every time we stare at those 6 crisp sides, we're glimpsing a universe where even chaos can wear a perfect mask. Deep in the frigid outskirts of our solar system, just beyond Neptune's orbit, lies a cosmic traffic jam, the Kuiper Belt, a sprawling disk of icy leftovers from the solar system's birth. But something strange happens around 50 astronomical units out. It's as if someone drew an invisible line in the cosmic sand, beyond which the number of objects plunges dramatically. This abrupt boundary, known as the Kuiper Cliff, is one of the solar system's most puzzling features. Why does the debris field suddenly vanish, and what unseen force could be responsible? The numbers don't add up. Based on our models of planetary formation, the Kuiper belt should extend smoothly for hundreds of astronomical units, gradually thinning out as you move farther from the Sun. Instead, observations reveal a sharp cutoff, like a cliff's edge around 50°. Some researchers argue this could point to an undiscovered planet lurking in the darkness, its gravity sweeping the area clean of debris. The idea isn't as far-fetched as it sounds. Similar gravitational shepherding shapes the inner solar system. Jupiter's gravity, for instance, prevents asteroids from coalescing into a planet between Mars and itself. Could a hidden world, perhaps several times Earth's mass, be doing the same beyond the Kuiper Cliff? But not everyone's convinced. Another camp proposes a more dramatic explanation, a close encounter with another star in our solar system's infancy. Picture this: a passing star billions of years ago, tugging at the outer Kuiper belt like a cosmic vacuum, stripping away everything beyond a certain distance. Simulations show such flybys were common in the young, densely packed Milky Way. If one occurred, it might explain not just the Kuiper Cliff, but also oddities like Sedna's elongated orbit, which can't be explained by the planets we know today. Then there's the wild card: orbital resonance. Neptune's gravity creates stable and unstable zones in the Kuiper belt, pushing objects into specific orbits while ejecting others. Some scientists suggest the cliff marks where these resonances run out of steam, leaving a stark divide between order and chaos. Yet even this theory struggles to account for the sheer abruptness of the drop-off, like flipping a switch rather than a gradual fade. The hunt for answers is heating up. New telescopes like the Vera Rubin Observatory will scan the outer solar system with unprecedented sensitivity, potentially spotting objects currently hidden in the glare of the Milky Way. Every new discovery chips away at the mystery, but the Kuiper Cliff remains a stark reminder of how much we don't know about our own cosmic backyard. Whether it's a hidden planet, a long-lost stellar intruder, or something even stranger, this invisible boundary challenges us to rethink the story of our solar system, one frozen fragment at a time. The cosmic microwave background is supposed to be the universe's baby picture, a near-perfect snapshot of the cosmos just 380,000 years after the Big Bang. Theoretically, it should look the same in every direction, a random splattering of hot and cold spots confirming the cosmological principle, the idea that the universe is homogeneous and isotropic with no special place or direction. But then there's the axis of evil, a spine-chilling name for a discovery so unsettling it makes physicists question everything we thought we knew about the universe's structure. Here's what rattled the scientific community. When researchers mapped the cosmic microwave background using satellites like WMAP and Planck, they noticed something bizarre. The largest fluctuations in temperature weren't randomly distributed as expected. Instead, they seem to align eerily with the plane of our solar system, as if the universe had quietly tipped its hat to Earth's little corner of space. The odds of this happening by chance, roughly 1 in 10,000. It's like tossing confetti in the air and watching it land in a perfect arrow pointing straight at your house. Skeptics were quick to suggest more mundane explanations. Could it be an artifact of the measurement process, contamination from our galaxy's dust? The Planck team ran exhaustive tests, subtracting foreground interference, tweaking algorithms, but the alignment stubbornly remained. Even more perplexing, this axis isn't just a visual quirk. It seems to split the universe into two hemispheres with slightly different average temperatures, a cosmic asymmetry that defies the very foundation of modern cosmology. If the cosmological principle is wrong, if the universe has a preferred direction, the implications are staggering. It could mean we're sitting in a rare, lopsided bubble within a larger, uneven cosmos. Some theorists propose wild alternatives, like pre-Big Bang relics warping space-time or our universe being one membrane among many in a higher dimensional multiverse. Others whisper about cosmic defects, ancient cracks in the fabric of reality left over from the universe's violent birth, but the most unsettling possibility: that we're seeing the fingerprints of something beyond our current physics. Just as the Michelson-Morley experiment's failure led to relativity, the axis of evil might be nudging us toward a paradigm shift, one where the universe isn't just stranger than we imagine, but stranger than we can imagine. Until we crack this code, the cosmos keeps sending us a cryptic message: there's far more to reality than meets the telescope. We think we've got the universe figured out until the numbers don't add up. Take ordinary matter, the stuff that makes up stars, planets, and even you. Scientists can calculate how much of it should exist based on the Big Bang's nuclear reactions, but here's the catch: about half of it is missing. Not dark matter, not some exotic particle, just regular protons and neutrons, the building blocks of everything we see. This cosmic accounting error is called the missing baryon problem, and it's forced astronomers to rethink where ordinary matter could be hiding. The search led to an unlikely suspect: vast, diffuse rivers of superheated gas weaving through the cosmos like phantom spiderwebs. Known as the warm-hot intergalactic medium, or WHIM, this material is so elusive it's practically invisible. Imagine steam from a boiling kettle, except spread across millions of light-years, with temperatures hitting millions of degrees. WHIM doesn't glow brightly like stars. Instead, it lurks in the spaces between galaxies, detectable only when it absorbs or distorts the light from distant quasars like cosmic fog. For decades, the evidence was circumstantial. Simulations predicted WHIM should exist, tracing the filamentary cosmic web predicted by dark matter's gravitational scaffolding. But catching it in the act, that required ingenuity. In 2017, the Planck satellite and other observatories finally found smoking gun evidence. By studying how WHIM subtly scatters the cosmic microwave background, like light bending through a prism, they pieced together its distribution. Even then, the gas is so tenuous that a cubic meter of it might contain just a single atom. Yet these whispers of matter add up. When tallied across the universe's sprawling filaments, WHIM could account for every missing baryon. The challenge now: mapping it in detail. New X-ray telescopes like a THEN are aimed to hunt WHIM's faint emissions, while advanced radio arrays probe its interaction with ancient light. Every observation brings us closer to balancing the cosmos's books and proving that sometimes what's missing isn't gone, it's just hiding in plain sight. Few cosmic sights are as strikingly unnatural as the Red Rectangle Nebula, a celestial structure so geometrically precise it looks like it was sketched with a ruler. Nestled 2,300 light-years away in the constellation Monoceros, this glowing trapezoid defies the usual chaos of stellar death with its crisp angles and vivid crimson hue. But its shape is only half the mystery. The nebula's spectrum reveals chemical fingerprints unlike anything else in the known universe, hinting at processes we've never witnessed. This isn't just a dying star's farewell, it's a cosmic laboratory where the rules of chemistry seem rewritten. At its heart lies a binary star system, HD 44179, locked in a gravitational dance that might hold the key to the nebula's eerie symmetry. Most planetary nebulae puff outward in spherical or spiral patterns, sculpted by a single star's death throes. The Red Rectangle, however, sports two sets of opposing ladder rungs, forming an X shape so precise it resembles a stained glass window. The likely culprit, a dense disk of dust and gas, funneled by the binary star's orbital motion into twin cones that project the nebula's sides like cosmic flashlight beams. Picture two figure skaters spinning while holding a giant hula hoop, their movements forcing debris into a rigid geometric plane. Then there's the color. The nebula's deep red glow comes not from typical ionized hydrogen, but from an obscure class of molecules called polycyclic aromatic hydrocarbons, complex carbon chains more commonly found in car exhaust or burnt toast. These shouldn't survive the harsh ultraviolet radiation of a dying star, yet here they thrive in abundance, fluorescing like neon signs. Even stranger, the nebula harbors unidentified infrared emission band spectral lines that match no known compound on Earth. Some theorists suggest they're from exotic carbon-based molecules, possibly even precursors to life's building blocks, forged in this unlikely stellar workshop. The red rectangle's secrets won't last forever. In about 1,000 years, a blink in cosmic time, its central stars will heat up, evaporating the dust and erasing those sharp edges forever. For now, it stands as a fleeting masterpiece, challenging our assumptions about how stars die and what kinds of chemistry the universe permits. Every odd angle and unexplained emission line whispers the same tantalizing question. If this is what we've found by chance, what other molecular wonders are hiding in the darkness, waiting to defy the textbooks? Imagine a bubble so vast it could swallow thousands of Milky Ways, yet inside, almost nothing. Welcome to the Boötes Void, a cosmic desert stretching 330 million light-years across, where galaxies are so sparse you could fly through it for eons without spotting a single star. Discovered in the 1980s during a galaxy survey, this void defies all expectations. While space is speckled with emptiness, most voids average 60 to 100 million light-years. The Boötes Void is a staggering outlier, so barren it feels less like a gap and more like someone erased a chunk of the universe. So how does something this empty even form? One camp argues it's just a freak accident in the cosmic lottery. The universe, after all, isn't perfectly uniform. Matter clumps and thins like froth on a cappuccino. Maybe the Boötes Void is simply the largest underdense region we've stumbled upon, a natural, if extreme, fluctuation, but the math tells a stranger story. For a void this size to exist by chance, the odds are worse than winning the Powerball a dozen times in a row. That's forced scientists to consider wilder possibilities. One theory points to dark energy's fingerprints. Could this void be evidence of an ancient battle where dark energy's repulsive force overpowered gravity in this region, pushing matter away like a cosmic bulldozer? Simulations show dark energy might create voids, but none as vast or empty as Boötes. Others propose it's a fossil from the early universe, a scar left when colossal sound waves called baryon acoustic oscillations rippled through the newborn cosmos, leaving behind empty pockets. Then there's the fringe idea: what if the void isn't empty at all but filled with something we can't see? Hypothetical structures like cosmic strings, defects in spacetime from the Big Bang might have carved out regions like this. Or perhaps advanced civilizations, yes, aliens again, could harvest galaxies on an unimaginable scale, leaving behind a void as their calling card. The truth might lie in the void's few surviving galaxies. These stragglers, clustered in thin filaments, act like breadcrumbs. By mapping their distribution, astronomers hope to backtrack the void's origins. Upcoming telescopes like the Vera Rubin Observatory could reveal fainter galaxies hiding in the darkness, tipping the scales toward natural causes or deepening the mystery. For now, the Boötes Void stands as a cosmic riddle. Is it a statistical hiccup, a relic of forces we barely understand, or something even stranger? One thing's certain: in a universe that's supposed to be full, emptiness has never been so fascinating. Mars should be a dead world, a frozen desert where chemistry long ago settled into quiet equilibrium. Yet something on the red planet refuses to follow the script. Methane, a gas that on Earth mostly comes from living organisms, keeps flickering in and out of detection like a cosmic game of peek-a-boo. The Curiosity rover's sniffing sessions have caught methane spikes up to 21 parts per billion, tiny by Earth standards but shocking for Mars. Here's the twist: these bursts vanish just as fast as they appear, sometimes within hours. And when the European Space Agency's Trace gas orbiter scanned the same regions from orbit, nothing, not a trace. This isn't just conflicting data. It's a full-blown scientific whodunit playing out across 2 spacecraft and 54 million kilometers of space. So where's the methane coming from if it's real at all? On Earth, 95% of atmospheric methane is biological, belched by microbes, cows, and rotting swamps. Could Mars host subterranean bacteria churning out these whiffs? It's not impossible. Methanogens, simple, ancient microbes, thrive in Earth's oxygen-free environments like deep caves or hydrothermal vents. Mars might hide similar oases beneath its rusty crust where liquid water could still linger. But biology isn't the only suspect. Geological processes like serpentinization, a reaction between water, carbon dioxide, and olivine rock, can produce methane without any life involved. Even meteorites sprinkling organic dust onto the surface might contribute when sunlight breaks them down. The real stumper is the methane's vanishing act. Mars's thin atmosphere should let methane linger for centuries, yet Curiosity's spikes disappear within days. One theory suggests an unknown chemical process is scrubbing the gas, perhaps highly reactive perchlorates in Martian soil acting like cosmic bleach. Another wild idea involves electric dust devils ionizing the air, creating temporary methane-destroying reactions. Or maybe the methane isn't vanishing at all, just slipping underground through porous rock layers, venting elsewhere like a planetary-scale game of whack-a-mole. Then there's the Trace gas orbiter's puzzling silence, orbiting 12 times higher than Curiosity's location. It might be seeing a different atmospheric layer where methane dissipates too quickly to detect. Alternatively, its instruments could be tuned to the wrong wavelengths, missing methane's spectral signature. The Rosalind Franklin rover, launching in 2028, aims to settle the debate with drills that can reach 2 meters underground, deep enough to potentially find microbes or their fossilized remains. Until then, Mars's methane remains a riddle wrapped in an enigma. Every whiff could be a sign we're not alone in the solar system, or just another reminder of how little we understand the red planet's hidden chemistry. One thing's certain: something on Mars is playing hard to get, and scientists won't stop hunting until they catch it in the act. In September 2020, astronomers made an announcement that sent shockwaves through the scientific community. They detected phosphine gas in the clouds of Venus. On Earth, this foul-smelling, flammable compound is almost exclusively produced by microbes thriving in oxygen-free environments like swamps and animal guts. Finding it on our scorching, acidic neighbor was like stumbling upon a smoking gun in a place where no fire should exist. The implications were staggering. Could floating microbial life be surviving 50 kilometers above Venus's hellish surface, riding the winds in temperate, Earth-like cloud layers? The discovery came from 2 telescopes, the James Clerk Maxwell Telescope in Hawaii and the Atacama Large Millimeter Array in Chile. Both picked up a spectral fingerprint unique to phosphine at parts per billion concentrations. The team, led by Professor Jane Greaves, ran exhaustive checks. Could volcanoes or lightning explain it? Unlikely. Venusian volcanism doesn't produce enough phosphorus, and lightning would require implausibly intense storms. Non-biological chemistry in Venus's sulfuric acid clouds. Laboratory tests showed the gas would be destroyed faster than it could accumulate. Every door seemed to close except one. Then came the backlash. Within months, other researchers challenged the findings. Some argued the signal could be sulfur dioxide masquerading as phosphine, a case of mistaken identity in the noisy dance of spectral lines. Others claimed the data processing might have amplified noise into a false positive. The original team stood firm, reprocessing their data and even identifying phosphine at higher altitudes where sulfur dioxide interference would be minimal. But the doubt lingered like a shadow. The debate hinges on Venus's brutal chemistry. At 900 degrees Fahrenheit with clouds of sulfuric acid, the planet's atmosphere is more industrial wasteland than microbial paradise. Yet Earth extremophiles bacteria thriving in nuclear reactors or boiling acid vents prove life can flourish in unthinkable conditions. If microbes exist in Venus's clouds, they'd need an entirely new biochemical playbook, possibly using sulfuric acid as a solvent instead of water. The stakes couldn't be higher. Confirming phosphine wouldn't prove life, but it would force us to rethink the boundaries of habitability. Upcoming missions like NASA's DFV-INCI probe and the European Space Agency's Envision aim to settle the debate, sniffing Venus's atmosphere directly or mapping its chemistry in unprecedented detail. For now, the phosphine mystery remains a tantalizing maybe, a single note in Venus's toxic symphony that sounds almost like a whisper of life. Whether it's a cosmic red herring or the first clue to extraterrestrial biology, one thing is certain: Venus just got a lot more interesting. Galaxies shouldn't exist without dark matter. It's the universe's invisible glue, the hidden scaffolding that holds galaxies together. Or at least that's what we thought until astronomers stumbled upon NGC 1052DF2, a ghostly galaxy that defies the rules. Floating 65 million light-years away in the constellation Cetus, this wispy cosmic enigma contains almost no dark matter at all. At first glance, that sounds like a technical curiosity until you realize it's like finding a skyscraper with no steel beams standing tall against gravity's pull. How does this even work, and does it mean our understanding of dark matter is flawed, or did we just misread the cosmic fine print? The discovery, announced in 2018, sent shockwaves through astrophysics. Most galaxies, including our Milky Way, behave as if they're stuffed with 5 to 10 times more mass than we can see, hence the need for dark matter. But when researchers measured DF2's rotation speeds and stellar motions, the numbers told a different story. The stars moved sluggishly, their velocities perfectly matching the gravity of visible matter alone. No extra pull, no hidden mass. It was as if someone had stripped the galaxy's dark matter skeleton clean away. Skeptics pounced immediately. Could it be a measurement error? DF2's sparse, translucent structure, technically an ultra-diffuse galaxy, makes distance calculations tricky. Get the distance wrong and you miscalculate the mass. Others suggested tidal stripping nearby galaxies might have ripped away its dark matter like cosmic vultures, but follow-up observations only deepened the mystery. In 2019, a second dark matter-deficient galaxy, DF4, was found nearby, followed by others. These weren't flukes, they were a pattern. The implications are explosive. If dark matter is real but can be separated from galaxies, it challenges the lambda CDM model, the reigning theory of cosmic structure. Maybe dark matter isn't as sticky as we thought, or perhaps galaxies can form through entirely unknown processes. On the flip side, if these galaxies never had dark matter to begin with, it raises even thornier questions. Did they condense from gas clouds in rare pockets where dark matter was absent? Or is there a yet undiscovered way to build galaxies without it? Then there's the contrarian view. What if dark matter doesn't exist at all, and DF2 is evidence for modified gravity theories like MOND? These theories tweak Newton's laws to explain galactic rotations without invoking invisible matter. But MOND struggles to explain cosmic-scale phenomena like the bullet cluster, where visible matter and gravitational effects clearly separate. DF2 might be a puzzle, but it's not yet a silver bullet. The hunt for answers is accelerating. New telescopes like the James Webb Space Telescope are probing these galaxies' faintest stars, while advanced simulations test whether dark matter can be kicked out by supernova or black holes. Every observation tightens the noose around this cosmic conundrum. Whether DF2 is a hole in our theories or a clue to something deeper, one thing's clear: the universe loves throwing curveballs, and this ghostly galaxy is one of its most baffling pitches yet. In a universe where galaxies typically spiral or clump into messy ellipses, Hoag's object stands out like a cosmic bullseye, a near-perfect ring of blue stars encircling a golden core, floating in the void like a celestial eye. Discovered in 1950 by astronomer Art Hoag, this rare ring galaxy defies every expectation, with its symmetrical structure so precise it almost looks engineered. Located 600 million light-years away in the constellation Serpens, it's one of fewer than 0.1% of galaxies that exhibit this bizarre, almost artistic form. But how does something so geometrically pristine emerge from the chaos of cosmic evolution? Theories abound, each as tantalizing as the last. One leading idea suggests a violent galactic collision, a smaller galaxy punching through the center of a larger one, sending shockwaves rippling outward like a stone dropped in water. These waves could compress gas and trigger star formation, creating that brilliant blue ring while leaving the central core undisturbed. Computer simulations show such encounters can produce ring-like structures, though none match Hoag's flawless symmetry. Another possibility is accretion, slow, steady cannibalization of gas and stars from a passing neighbor, gradually sculpting the material into a ring over billions of years. Yet Hoag's object shows no signs of a recent collision, no messy debris or distorted trails. It's eerily clean, as if the universe handed it a blueprint and said, "Build this." Then there's the enigma of its core. Unlike most ring galaxies, where the center is a chaotic mix of young and old stars, Hoag's core is a serene, ancient ball of yellow giants, stars nearly as old as the universe itself. The ring, by contrast, sparkles with newborn blue stars, a stellar nursery fueled by pristine gas. This stark duality suggests two distinct epochs of star formation, separated by billions of years of silence. What paused the galaxy's evolution, only to restart it in a perfect circle? Some speculate the core could be the remnant of a long-dead quasar, its central black hole gone quiet, while the ring represents a second act, a rebirth fueled by some forgotten cosmic trigger. Adding to the mystery, Hoag's object isn't alone in its strangeness. In 2021, astronomers spotted another ring galaxy dubbed Hoag's twin, with nearly identical structure. This raises a spine-tingling question. Are these rare objects the result of some universal fluke, or is there a hidden mechanism, a yet undiscovered law of galactic dynamics, that occasionally produces these celestial masterpieces? The answer might lie in the gaps between rings. Recent Hubble images reveal faint, delicate bridges of stars arcing around Hoag's object, possible relics of a past interaction too subtle for our models to predict. Upcoming telescopes like the James Webb Space Telescope could dissect these filaments in infrared, searching for chemical fingerprints that betray the galaxy's violent or serene history. For now, Hoag's object remains a cosmic riddle, a reminder that even in a universe governed by chaos, beauty can emerge in the most unexpected forms. Whether it's the scar of a forgotten collision or the signature of some deeper physics, this galactic oddity challenges us to rethink how perfection can arise from the void, one luminous ring at a time. The universe isn't just a random scattering of galaxies, it's a meticulously woven tapestry, a sprawling network of filaments and voids that stretch across billions of light-years like threads of an invisible spiderweb. This cosmic web, as astronomers call it, is the largest structure in existence, a skeleton of dark matter and gas where galaxies cling like dewdrops on a silk strand. But how did this intricate architecture emerge from the formless chaos of the Big Bang? And why, despite our most advanced supercomputers, does nature's blueprint still outmatch our simulations? Rewind to the universe's first moments. After the Big Bang's explosive birth, space was a nearly uniform soup of particles, hotter than the core of a star. But buried in that plasma were tiny quantum fluctuations, random ripples in density no larger than 0.001%. Over millions of years, gravity amplified these faint wrinkles, pulling matter into denser knots while leaving emptier regions to stretch into voids. Dark matter, invisible and pervasive, acted as the universe's scaffolding, its gravity sculpting the first tendrils of the cosmic web. Ordinary matter, the stuff of stars and planets, simply followed, flowing along these hidden channels like water filling grooves in sand. The problem, when scientists try to recreate this process in supercomputer simulations, something's off. Programs like Illustris TNG and Eagle produce cosmic webs that look almost right, but the details betray glaring gaps. Real filaments are sharper, more defined, with galaxies clustered more densely along their spines than models predict. Voids, too, are emptier in reality, more like bubbles of nothingness than the fuzzy transitions simulations generate. It's as if the universe had access to a finer brush, painting structures with precision our code can't yet match. One leading theory points to feedback cycles we're still deciphering. Supermassive black holes, for instance, blast energy into their surroundings like cosmic blowtorches, heating gas and preventing it from collapsing into new stars. Galactic winds, torrents of particles flung out by supernova, might push matter into filamentary walls. Even magnetic fields, often overlooked in models, could play a role, channeling gas into tighter streams. Yet when these factors are added to simulations, the results still don't quite mirror reality. Perhaps the biggest wild card is dark matter itself. Most simulations assume it's cold, slow-moving and clumpy. But what if it's warm, with particles just fast enough to smooth out small-scale structures? Or what if dark matter interacts with itself through some unknown force, subtly reshaping the web's geometry? Alternative theories like modified gravity throw another wrench into the works, suggesting gravity behaves differently on cosmic scales, eliminating the need for dark matter entirely, though these struggle to explain phenomena like the bullet cluster. Then there's the enigma of baryonic asymmetry. The cosmic web should mirror the distribution of both dark and ordinary matter, yet observations show galaxies prefer certain filament junctions over others, as if drawn to invisible crossroads. Some researchers speculate that quantum effects in the early universe imprinted a hidden pattern, a primordial blueprint guiding where galaxies would eventually bloom. Others wonder if cosmic inflation, the universe's exponential expansion in its first fraction of a second, planted seeds we've yet to fully decode. The stakes couldn't be higher. The cosmic web isn't just a curiosity, it's the stage upon which galaxies evolve, the highway system directing their motions. Unlocking its mysteries could reveal why we find ourselves in a spiral arm of the Milky Way rather than adrift in a void, or whether other web-like structures exist in unseen dimensions. Upcoming telescopes like the Roman Space Telescope aim to map the web in 3D, charting billions of galaxies to expose its finest threads. Meanwhile, quantum physicists simulate the universe's first trillionth of a second, seeking those initial ripples that grew into the web we see today. For now, the cosmic web remains a masterpiece half-finished, its grand design clear in broad strokes but devilish in detail. Every mismatch between simulation and observation is a clue, a whisper from the universe that there's more to the story, and that the largest structure in existence still holds secrets written in dark matter's ink. Somewhere in the vast emptiness of space, atomic nuclei are being hurled across the universe with energies so extreme they defy all known physics, packing the punch of a fast-pitched baseball into a single subatomic particle. These are ultra-high-energy cosmic rays, and the most powerful among them, like the infamous "Oh my God" particle detected in 1991, carry kinetic energy equivalent to dropping a brick from waist height. Concentrated into a speck smaller than an atom, when scientists first calculated its energy, 320 exa-electron volts, millions of times more powerful than anything produced in human particle colliders. Their reaction was immortalized in its name. So where do these microscopic cannonballs come from? That's the problem. At these energies, cosmic rays should be crippled by the cosmic microwave background, the afterglow of the Big Bang that fills space like a fog. Colliding with these ancient photons, ultra-high-energy particles ought to lose momentum over long distances, a phenomenon called the Greisen-Zatzepin-Kuzmin cutoff. Yet here they are, arriving on Earth with undiminished fury. Either their sources are shockingly close within our galactic neighborhood, or something is fundamentally wrong with our understanding of particle physics. The prime suspects, active galactic nuclei, where supermassive black holes launch jets of plasma at near light speed, or perhaps gamma-ray bursts, the universe's most violent explosions. The trouble is, no known event in our cosmic backyard matches the timing and direction of these rays. The oh my god particle, for instance, seemed to originate from a void, an area of space conspicuously empty of extreme astrophysical phenomena. Enter the Pierre Auger Observatory in Argentina, a sprawling detector the size of Rhode Island designed to catch these rare particles in action. When a cosmic ray slams into Earth's atmosphere, it triggers an air shower, a cascade of secondary particles that spread like a conical fireworks display. Auger's 1,600 water tanks and fluorescence detectors capture these fleeting bursts, tracing the original ray's energy and trajectory. After decades of data, patterns are emerging. Some rays cluster near active galaxies like Centaurus A, while others point towards supermassive black holes merging in the distant universe, yet the mystery deepens. Many high-energy events still come from nowhere in particular, and the highest energy rays remain tantalizingly rare. Only a few per century strike each square mile of Earth. New detectors, like the planned giant radio array for neutrino detection in Europe, aim to expand the hunt. But for now, these particles stand as cosmic conundrums, proof that somewhere in the void, nature is running a particle accelerator we don't yet understand, one that flings atomic fragments with forces beyond anything we can replicate. Every time one strikes, it's not just a detection, it's a challenge from the universe itself, daring us to rethink the limits of energy, space, and time. Imagine measuring the speed of a car twice, once with a radar gun and once by timing it between mile markers, and getting two wildly different answers. Now replace that car with the entire universe, and you've got the Hubble tension, a cosmic speedometer crisis that's tearing at the seams of modern cosmology. Here's the problem: depending on where and how we measure it, the universe's expansion rate, the Hubble constant, gives us two conflicting numbers. It's as if the cosmos is playing a cruel joke on physicists, revealing one rate when we study nearby galaxies and a noticeably slower one when we peer back to the infant universe. This isn't just a rounding error, it's a full-blown discrepancy that could force us to rewrite the rules of space-time itself. Let's break down the mismatch. The local method uses pulsating stars called Cepheid variables and cataclysmic supernova as cosmic yardsticks. By tracking their brightness and distances in nearby galaxies, astronomers calculate an expansion rate of roughly 73 kilometers per second per megaparsec. But when we study the afterglow of the Big Bang, the cosmic microwave background through missions like Planck, the early universe whispers a slower number, 67. That gap might sound trivial, but after 13.8 billion years of compounding, it implies a universe noticeably larger or smaller than our models predict. Either we've made a colossal measurement error unlikely given decades of cross-checking, or something fundamental is missing from our understanding of cosmic evolution. Enter dark radiation, a hypothetical wildcard that might bridge the divide. This isn't dark matter or dark energy, but a shadowy cousin, fast-moving particles like sterile neutrinos that barely interact with normal matter. If they flooded the early universe, they could have subtly altered how quickly matter clumped together, tweaking the cosmic microwave background signature without leaving traces in local measurements. Think of it as adding an invisible current to a river. The water's speed changes, but you'd never spot the cause from the shore. Alternative theories stretch even further. Maybe dark energy isn't constant but evolves over time, stronger in some epochs than others. or perhaps gravity itself behaves differently on cosmic scales, a radical idea that would upend Einstein's relativity. Even the fabric of space-time isn't safe from scrutiny. Some suggest strange quantum fluctuations in the early universe created microscopic knots that now skew our measurements. The stakes: this isn't just academic nitpicking. If the Hubble tension is real, it means our standard model of cosmology, the Lambda-Cidium framework that's guided astrophysics for decades, is incomplete. Upcoming telescopes like the Nancy Grace Roman Space Telescope aim to settle the debate with hyper-precise measurements of distant supernova and gravitational lenses. Meanwhile, labs like CERN hunt for dark radiation candidates in particle accelerators, slamming protons together to recreate conditions a trillionth of a second after the Big Bang. For now, the Hubble tension remains a cosmic tug-of-war between data and theory, a reminder that even our best models are provisional sketches of a universe still full of surprises. Whether it's dark radiation, phantom energy, or something entirely unimagined, one thing's clear: the cosmos is expanding, and so is our list of questions about how and why it's doing so at all. What if the universe's greatest mysteries, dark matter, cosmic ray anomalies, even the Hubble tension, are all whispers of something far stranger, a shadow realm of reality where physics as we know it simply breaks down? Enter unparticle theory, one of the most radical ideas in modern physics, proposing the existence of an invisible sector of reality governed by rules so alien they make quantum mechanics look like child's play. This isn't just another particle or force, it's an entirely new kind of stuff, dubbed unparticles, that doesn't play by the standard rulebook of mass, charge, or spin. And if it's real, it could be the key to unlocking nearly every cosmic puzzle we've encountered so far. The idea was born in 2007 when physicist Howard Georgi asked a deceptively simple question: what if certain particles don't behave like particles at all? Normally, particles fit neatly into categories: electrons, quarks, photons, each with defined properties. But unparticles defy this. They're scale invariant, meaning they look the same no matter how closely you zoom in or out, like a fractal that never resolves into clear edges. Picture trying to weigh a cloud. The more you try to pin it down, the less it behaves like a solid object. Unparticles occupy a bizarre middle ground between particles and waves, with fractional, effective masses that shift depending on how you observe them. This isn't just abstract math. It could explain why dark matter refuses to show up in our detectors. Unparticles wouldn't interact via the strong, weak, or electromagnetic forces. They'd communicate through their own hidden sector, leaving only faint gravitational ripples. Unlike WIMP or actions, they wouldn't annihilate or decay in ways we're used to. Instead, they might flit in and out of our reality like cosmic phantoms, detectable only through their gravitational fingerprints on galaxies and galaxy clusters. The theory gets wilder. Unparticles could be behind ultra-high-energy cosmic rays, those atomic projectiles that hit with impossible force. If these particles occasionally leak into our dimension, they might carry energy scales far beyond what our accelerators can produce, like droplets from a waterfall we can't see. Even the Hubble tension might find a solution here. Unparticle interactions in the early universe could have subtly warped spacetime's expansion, leaving us with conflicting measurements today. Critics argue the theory is too flexible, a kitchen sink for unexplained phenomena. But supporters counter that unparticles naturally emerge from certain string theory models, where higher dimensional physics manifests as scale-free behavior in our 3D world. Experiments are already hunting for hints. Particle colliders like the LHC look for energy imbalances in collisions, while astrophysical surveys scan for anomalous gravitational lensing patterns that don't align with ordinary matter. The real magic of unparticle theory isn't just its potential answers, it's how it redefines what we consider possible. If validated, it would mean the universe isn't just built from particles and waves, but from entities that defy both, lurking in the shadows of reality. Every unexplained cosmic oddity becomes a potential clue, a breadcrumb leading us toward a frontier where physics as we know it dissolves into something infinitely stranger. And that's the most thrilling possibility of all, not just solving mysteries, but discovering a whole new layer of the universe we never knew to look for. From the wow signal's cryptic blip to the ghostly pull of the Great Attractor, we've journeyed through cosmic puzzles that defy even the sharpest scientific minds. These aren't just gaps in our knowledge, they're invitations to rethink reality itself. Every unexplained phenomenon, from dark matter's invisible grip to Venus's disputed phosphine, isn't a dead end but a detour sign pointing toward discoveries we haven't yet imagined. The universe doesn't owe us easy answers, and that's what makes exploration so thrilling. Each mystery is a reminder that science isn't about having all the solutions, it's about asking better questions. Consider how far we've come already. A century ago, we didn't know galaxies existed beyond the Milky Way. Today, we're wrestling with the holographic nature of black holes and hunting for unparticles in the quantum foam. The Hubble tension isn't just a disagreement about numbers. It's evidence that our cosmic map still has blank edges waiting to be filled. Even failures like the fleeting detections of Martian methane or the silent follow-ups to Oumuamua push us to build better tools, sharper theories. Every "that's weird" moment in astronomy has historically led to breakthroughs, from Einstein's relativity to the discovery of dark energy. So what's next? Maybe you'll be the one to spot a pattern in fast radio bursts, or write the paper that finally cracks the black hole information paradox. The greatest enigmas aren't just for PhDs, they belong to anyone who looks up and wonders. Drop your favorite mystery in the comments. Is it the hexagonal storm on Saturn, the missing baryons, that eerie axis of evil? Or hit subscribe to join us as we chase the next cosmic head-scratcher. Because the universe isn't done surprising us, and the best discoveries always start with a simple question. Wait, why does it do that?